Hello, this is Miss Moore, and today during chemistry we will be continuing our stoichiometry discussion. Specifically today we'll be talking about the limiting reagent, also known as the limiting reactant. Today's essential question: how is the limiting reactant in a reaction determined? Today you will want your periodic tables, your unit conversion tables, and your calculators handy. All right, let's do this. We'll start by what is a limiting reagent, or I guess it could also be called the limiting reactant. Okay, so far, all of the reactions and calculations we've talked about describe an ideal situation, meaning we have the perfect amount of reactants, of each of the reactants, to make the perfect amount of product. There's no problems, there are no issues. That's what I mean by an ideal situation. And of course, life is never ideal. So in a chemical reaction, an insufficient quantity of any of the reactants will limit the amount of product that forms. So by insufficient, what does that mean? Like not enough. So if we have not enough of one of the reactants, it will limit how much product we can make. So let's take, for example, let's say I was going to make peanut butter sandwiches. And I had a whole jar of peanut butter and a whole jar of jelly. So thinking about a whole jar of peanut butter and a whole jar of jelly, you would assume I could make a lot of peanut butter sandwiches. However, I only have 3 pieces of bread. So my reactants are peanut butter, jelly, and bread. And the product would be the peanut butter sandwich. So how many peanut butter sandwiches could I make if I have a whole jar of peanut butter, a whole jar of jelly, and 3 pieces of bread? Well, I could make 3 peanut butter sandwiches, even though I have a whole jar of peanut butter and a whole jar of jelly. Why? Because the number of pieces of bread is going to limit how many peanut butter sandwiches I can make. So we have an insufficient amount of bread to make more than 1 peanut butter sandwich. So the definition of a limiting reagent or limiting reactant is the reactant that is completely used up during a reaction. So in our peanut butter and jelly sandwich example, the bread was our limiting reactant, right? We used it up even though we had more peanut butter and jelly. So in theory, you would think we could make a lot of peanut butter and jelly sandwiches, but we were limited by the amount of bread. So that's our limiting reactant. So a limiting reactant limits the amount of the other reactants that can participate in the reaction. So think about that. How much peanut butter and jelly can I actually use if I only have 3 pieces of bread? Right? There's going to end up being a lot more peanut butter and jelly left over that's not going to be part of our peanut butter and jelly sandwich reaction. The limiting reactant also limits the amount of product that can be formed, right? In our reaction, our peanut butter and jelly sandwich reaction, we could only make 1 peanut butter and jelly sandwich because our bread limited the amount we could make. The reaction stops when the limiting reactant is used up. Even though we had extra peanut butter and jelly, we had to stop making peanut butter and jelly sandwiches because we had used up our bread. All right, and that brings us to excess reagent. Excess reagent or reactant is what is not used up during the reaction. It's our leftovers. And in our example, what was left over? Our peanut butter and our jelly, right? We had lots and lots. We had a peanut butter and jelly left over. That was our excess. Those were, I guess I should say, those were our excess reagents. So again, a limiting reagent is the thing that makes the reaction stop, basically, because we've run out of it. Even though we could end up with excess, other stuff, other reactants are left over. Okay, so those are the definitions of limiting and excess reagents. All right, so now that we know the definitions of limiting and excess reagents, let's get to the essential question is, how do we calculate that? So, how to determine the limiting reagent? So what we're going to do is we're going to use stoichiometry, the stuff we've been doing so far, to determine the mass of product that can be produced from each of the reactants. Okay, so we're gonna calculate how many sandwiches we can make with the bread we have. We're going to calculate the number of sandwiches we can make with the amount of peanut butter we have, and we're going to calculate the number of sandwiches we can make for the amount of jelly we have. Okay, now using my peanut butter and jelly example, it's pretty easy just to sort of think about in your mind, but when we're talking about chemicals in a chemical reaction, you actually need to do the calculations. If you have more than one product, you only need to do the calculations for one of the products. And it doesn't matter, let's put that up there. It doesn't matter which product you use, but use the same product for each reactant. If the question asks you how much of a specific product was created, of course, pick that product. All right, so now we'll do our stoichiometry for each of our reactants. And the reactant that makes the least product is the one that's limiting. Because the product, whatever product we're calculating, nope, let's take step back. Once the reactant that we're thinking about has been used up, that's the most amount of product you can make. So the amount of product formed from the limiting reagent is the maximum amount of product that can be formed. Okay, I know this might seem a little confusing, but hopefully going through a practice problem, it won't be quite so bad. So let's try this. Okay, so our example here is that we have a 2-gram sample of ammonia, which is mixed with 4 grams of oxygen, which is the limiting reagent or reactant. Okay, so we need to do 2 different stoichiometry problems. One where our known is going to be ammonia, and the second one where our known is going to be oxygen. And then for both problems, we need to pick an unknown. We could use NO or H2O. I'm going to go ahead and pick NO because, because it's the first one. Okay, so for my first known, I'll put my known here, we'll make it ammonia. So we have a 2.00 gram sample of ammonia. And my unknown is going to be NO. And again, I could have picked water if I wanted to. All right, so we've identified our known and our unknown for our first problem. So now what we need to do is set up the grid and put our known in the grid. And my known is going to be 2 grams of ammonia over 1. All right, so the next thing we need to do is pick an equality. So right now in our grid, we're at grams ammonia, which was our known, right? So we need to find an equality that starts with grams known. So going up to our equality, it looks like that one would be a good one to use, the molar mass of the known. Remember, molar mass is in grams. So molar mass of the known equals 1 mole of the known. So our known is NH3, which means to get the molar mass, we're going to add up the mass of 1 nitrogen, which is 14.01 grams, and 3 hydrogens, which is 1.01 grams times 3. So we end up with 17.04 grams of ammonia equals 1 mole of ammonia, or molar mass of known equals molar mass equals 1 mole of the known. Okay, so now we pick what goes on the bottom by looking at the units and the molecule, and we're at grams NH3, so we want to be able to cross that out, which means grams NH3 needs to go on the bottom. So we'll do that. And whatever's left over, in this case 1 mole NH3, goes on the top. Okay, now we need to cross out our units, check and make sure they cross out. So grams NH3 indeed crosses out grams NH3, and we're left at mole NH3, which is not what we were looking for. We were looking for NO. And actually, I should have made that a little more clear. That was supposed to be grams NO. Okay, so where are we at now? We're at mole NH3, which is our mole known. So let's find an equality that starts with mole known. That would be our second equality here. Blank mole known equals blank mole unknown, and we get that information from the balanced equation. So our known is NH3, and our unknown we've decided was NO. So we need to put those in our equality, setting them up so our units cancel out. And since we're at mole NH3 now, we want that one at the bottom. So for mole NH3, and on the top is going to go for mole NO. All right. We now need to cross out our units, make sure they cross out. So mole NH3 crosses out mole NH3. We're at mole NO, which is the right molecule but the wrong unit. So we got to do another step. We're at mole NO, which is mole unknown. So which one of our equalities starts with mole unknown? Mole unknown equals molar mass of unknown. So we're going to use that one. So 1 mole of our unknown is NO, and the molar mass of the unknown is the mass of N, 14.01 grams, and the added to the mass of oxygen, which is 16.00 grams, giving us a mass of 30.01 grams of NO. All right, now to identify what goes on the top or the bottom, we have mole NO at the top, so we need that one at the bottom so that they cross out. And that means whatever's left over goes at the top. Oops, a little squishy there. Hope you can see that. All right, let's cross out our units. Mole NO crosses out mole NO. We're left at grams NO, which is what we were looking for. So now all we got to do is multiply and divide and stuff. So when we multiply across the top, we get 2 times 4 times 30.01. And if I'm using my calculator correctly, I got 240.08 grams NO. And when I multiply across the bottom, 17.04 grams times 4, I come up with 68.16. We'll divide, giving us, hopefully, 3.5223, and so forth, grams NO. All right, let's check sig figs. So our given is 3 sig figs, and then we calculated molar mass here, so that's 4 sig figs. We don't use those for sig figs. Our second molar mass also 4 sig figs. So we're going to have 3 sig figs in our answer. So that means when we start with 2 grams of NH3, we can make 3.52 grams of NO. Okay, so that's step 1. Let me clean this up a bit. Okay, so now I have a little bit of room to work. So, now when we our ammonia, our 2.00 grams of NH3 gave us 3.52 grams of NO. Okay, so that is our first answer. Sorry about that. Let's try that again. Now we need to do this problem again. Let's get rid of this stuff. Now we need to do the whole problem again, but this time we need to do it with our 4 grams of oxygen. So we'll set up our grid again. And we'll have 4 grams of oxygen over 1. Oh, I guess I should identify my known and my unknown. So my known is 4 grams of oxygen. And my unknown is still going to be grams of NO. All right, so we're going to go through this whole process again. So step 1, we're at grams of oxygen, which is our grams known. So clean up that mess. Which one starts with grams known? Molar mass of known equals 1 mole of known. So molar mass of oxygen, 1 oxygen is 16.00 grams, but we have 2 of them. So 32.00 grams O2 equals 1 mole O2. And to figure out which one goes at the bottom, we want to match up and be able to cross out. So grams O2 is at the top, so we want grams O2 at the bottom. That means that mole O2 goes at the top. All right, let's cross out some units. Grams O2, cross out grams O2. We're left at mole O2, but we're looking for mass NO. So we're not done yet. We're at mole O2, which is our known. So which one of these starts with mole known? Mole known equals mole unknown from the balanced equation. All right, so in our balanced equation, our known this time is 5O2, and our unknown is still 4NO. So on the bottom here, we're going to put our known, 5 mole O2, and on the top, we will have 4 mole NO. All right, let's cross out our units. Mole O2 crosses out mole O2. We're at mole NO. We've got the right unit, but we need to still go to mass NO or mass unknown. So we need to find an inequality that starts with mole unknown, which is 1 mole unknown equals the molar mass of unknown. So 1 mole unknown, or 1 mole NO, equals the molar mass of NO, which is adding up N, the mass of N and the mass of O, which we did just a minute ago. So that's 30.01 grams NO. And because we have mole NO at the top, we need mole NO at the bottom, so they cross out. All right, let's cross out our units. Mole NO crosses out mole NO. We'll double check. We're at grams NO, which is what we were looking for. So now let's do some multiplying and dividing and stuff. So if I multiply across the top, 4.00 times 4 times 30.01, I got 480.16 grams NO. And multiplying across the bottom, 32.00 times 5 times 1, I got 160. And when I divide, I get 3.001 grams NO. And last step, of course, is sig figs. So our given has 3 sig figs. And then we have 2 masses, which we also use for sig figs. They're both 4. So we are going to use 3 sig figs. So we have 3.00 grams NO. All right, let's erase a little bit of this stuff, clean it up a little bit. And when we start with 4 grams of O2, we produce 3.00 grams of NO. So, which one now is limiting? Starting with 2 grams of NH3 and assuming unlimited O2, we ended up with 3.52 grams of NO. Starting with 4 grams of O2 and assuming unlimited NH3, we produce 3 grams of NO. That means that our O2 is limiting. That's because the O2 made less NO, which means it ran out first. Okay, so our question was, which is the limiting reagent or reactant? It's O2. Hopefully that makes sense. And we'll now move on to calculating excess reactant. Alrighty, on to determining the amount of excess reagent. In all honesty, this is the part where people get a little lost. So as we're going through this, really think about it. All right, so to determine the amount of excess reagent, and what I mean by excess reagent is, like we go back to our peanut butter and jelly example, our bread was the limiting, excess is the stuff that's left over, like our peanut butter and jelly. So what we want to try to do is figure out exactly how much peanut butter and how much jelly is left over. All right, so to determine the amount of excess reagent that did not react, you first need to determine how much did react. So for example, how much exactly peanut butter and jelly did we use? So to do that, you do mass-mass conversions with the mass of the limiting reagent as the given, and then calculate the mass of the excess reagent. So if you think about it, it's like saying, if I used 3 pieces of bread, right, because that was our limiting, how much peanut butter and jelly? No, I didn't end up using 3 pieces of bread, did I? I used only 2. If I used 2 pieces of bread, how much peanut butter and jelly did I actually use? Okay, so our bread was our known, and the peanut butter and jelly is going to be my unknown. Okay, the answer will be how much excess reagent was used. And then if we want to know how much was left over, subtract how much was used, this guy, from how much you started with. Okay, so we're going to use basically our same question, just go a little further with this. So if I have a 2-gram sample of ammonia is mixed with 4 grams of oxygen, how much excess reactant remains after the reaction is stopped? And remember from the previous problem, our O2 was limiting, which means that our NH3 is our excess. Yep, sorry. All right, so that means that we're going to use O2 as our known. Okay, so our 4 grams oxygen is our known, and our unknown is going to be our ammonia. Now, I realize they told us in the problem how much ammonia was given, but that's not what we're trying to figure out. We're trying to figure out how much ammonia was actually used, which is why it's going to be our unknown. So this is our unknown. So grams of ammonia. And this guy here is our known. All right, so now we just do our normal stoichiometry steps. So we write our grid, and we write our known in the grid, which is 4 grams of O2 over 1. And we check where we're at. We're at grams O2, which is our grams known. So which equality has grams known in it? Starts with grams known, sorry. Molar mass of known equals 1 mole of known. So molar mass of O2, 16 plus 16 is 32.00 grams O2 equals 1 mole O2. And I forgot this was supposed to be yellow. Let's change that real quick. All right, so we're going to put grams O2 on the bottom so we can cross out the grams O2 here. So mole O2 goes at the top. All right, now we cross out our units. Grams O2 crosses out grams O2. We're left at mole O2. We were looking for grams NH3, so we're not done yet. So we're at mole known, because O2 was our known. So which equality starts with mole known? The middle one here. Mole known equals mole unknown from the balanced equation. So in our balanced equation, our known is O2. And our unknown is NH3. So I'm going to put at the bottom 5 mole O2, so we can cross out mole O2. And the top will be 4 mole NH3. All right, let's cross out our units and stuff. So mole O2 crosses out mole O2. We're left at mole NH3. We were looking for mass NH3, so we're not quite done. So we're at mole known, and we want to go to mass known. So which equality starts with mole unknown? 1 mole equals molar mass. 1 mole of unknown equals molar mass of unknown. So our unknown is NH3. So we're going to have 1 mole of NH3 equals the molar mass of NH3, which is 14.01 plus 3 1.01s, giving us 17.04 grams NH3. All right, so you have to set these up in the grid so that the units cancel out. So mole NH3 goes at the bottom. grams NH3 goes at the top. We'll cancel out our units. Check where we're at. We're at mass NH3 or mass unknown, which is what we were looking for. So the next thing we need to do is multiply across the top, multiply across the bottom, and divide. So when we multiply across the top, we're multiplying 4.00 times 4 times 17.04. I got 272.64 grams NH3. And multiplying across the bottom, 32.00 times 5, I got 160. Giving us 1.703125 grams NH3. And then, of course, sig figs. Our given has 3 sig figs. We also need to look at our masses. We have 4 and 4, so 3 sig figs. So that gives us 1.70 grams NH3. So what does that mean? Let me move this a little bit. Give me a little bit more room. Okay, what this means is that we used 17.0 grams of NH3. The question, however, asked us how much remains after the reaction. Okay, so what we're going to do is we're going to look at how much we started with. We started with 2.00 grams. So we started with 2.00 grams of NH3. That's how much we started with. We used 1.70 grams of NH3. So to figure out how much remains, we just subtract those. And that gives us let's see, 0.30 grams NH3. That is how much is left over, or how much remains after the reaction. Okay, and then if we look at sig figs, remember when you're adding or subtracting, you look at digits after the decimal. So we need 2 digits after the decimal. So there you go. All right, folks, I know that was a long one and a little tricky, but the truth is you know how to do each step. You just have to do a little bit more thinking. All right, that's it for today. Have a good one.